Hello everyone, and welcome to my channel. This channel is for educational purposes, and we look at theories of everything. In particular, today is our 480th video on the reciprocal system of theory from Dewey B. Larson. And we're going into this deep, and hopefully will help you kind of appraise this theory of everything and how you can use it to benefit your life. Because, with a theory of everything, it might seem like it's about one subject or another, but it can be applied universally. And so today we're going over chapter 10 of Larson's book, Basic Properties of Matter. Chapter 10 is on electrical resistance. Now, before you turn this off and say you're not interested in electricity or the basic properties of matter, think kind of more broadly that, this is a generalized theory. The reciprocal system is a generalized or a system of theory. You can plug it into any subject that you'd like. And to see how Larson plugs it into chemistry and to electrical resistance in particular sheds light on how it can be plugged into other subjects. So you have to kind of get a grasp of the whole theory, how he applies it to chemistry, astronomy, metaphysics, economics, psychology, and how some of his followers plugged it into even studies even further afield, to be able to kind of grasp its potential and how you can use it in your own life. Okay, now, if you don't know anything about the reciprocal system, you can try to glean something from this episode here, but you can also go back to any of my first 474 videos on this subject, and I give at least a relatively thorough explanation of the reciprocal system and how it works. But now I pretty much am going to assume that you know something about it, that you know the basic idea behind the reciprocal system, the universe of motion. And I'm just going to start in with the reading from chapter 10. Okay, chapter 10, electrical resistance. While the motion of the electric current through matter is equivalent to motion of matter through space, as brought out in the discussion in chapter 9, the conditions under which each type of motion is encountered in our ordinary experience emphasize different aspects of the common fundamentals. In dealing with the motion of matter through extension space, we are primarily concerned with the motions of individual objects. Newton's laws of motion, which are the foundation stones of mechanics, deal with the application of forces to initiate or modify the motions of such objects. And with the transfer of motion from one object to another, our interest in the electric current, on the other hand, is concerned mainly with the continuous aspects of the current flow. And the status of the individual objects that are involved is largely irrelevant. The mobility of the spatial units in the current flow also introduces some kinds of variability that are not present in the movement of matter through extension space. Consequently, there are behavior characteristics or properties of material structures that are peculiar to the relation between these structures and the moving electrons. Expressing this in another way, we may say that matter has some distinctive electrical properties The basic property of this nature is resistance. As pointed out in Chapter 9, resistance is the only quantity participating in the fundamental relations of current flow that is not a familiar feature of the mechanical system of equations, the equations that deal with the motion of matter through extension space. Present-day ideas as to the origin of electrical resistance are summarized by one author in this manner. Ability to conduct electricity is due to the presence of, this is a quote, ability to conduct electricity is due to the presence of large numbers of quasi-free electrons which under the action of an applied electric field are able to flow through the metallic lattice. Disturbing influences impede the free flow of electrons, scattering them and giving rise to a resistance. As indicated in the preceding chapter, the development of the theory of the universe of motion arrives at a totally different concept of the nature of electrical resistance. The electrons, we find, are derived from the environment. It was brought out in Volume 1 that there are physical processes in operation which produce electrons in substantial quantities, and that although the motions that constitute these electrons are, in many cases, absorbed by atomic structures, the opportunities for utilizing this type of motion in such structures are limited. It follows that there is always a large excess of free electrons in the material sector of the universe, most of which are uncharged. In this uncharged state, the electrons cannot move with respect to extension space because they are inherently rotating units of space, and the relation of space to space is not motion. In open space, therefore, each uncharged electron remains permanently in the same location with respect to the natural reference system, in the manner of a photon. In the context of the stationary spatial reference system, the uncharged electron, like the photon, is carried outward at the speed of light by the progression of the natural reference system. All material aggregates are thus exposed to a flux of electrons similar to the continual bombardment of photons by radiation. Meanwhile, there are other processes to be discussed later whereby electrons are returned to the environment. The electron population of a material aggregate such as the Earth therefore stabilizes at an equilibrium level. These processes that determine the equilibrium electron concentration are independent of the nature of the atoms of matter and of the atomic volume. The concentration of electrons is therefore uniform in electrically isolated conductors where there is no current flow. It follows that the number of electrons involved in the thermal motion of atoms of matter is proportional to the atomic volume, and the energy of that motion is determined by the effective rotational factors of the atoms. The atomic volume and the thermal energy therefore determine the resistance. Those substances whose rotational motion is entirely in time, those of division 1 and 2, have their thermal motion in space, in accordance with the general rule governing addition of motions, as set forth in Volume 1. For these substances, zero thermal motion corresponds to zero resistance, and the resistance increases with the temperature. This is due to the fact that the concentration of electrons, or units of space, in the time component of the conductor is constant for any specific current magnitude, and the current therefore increases the thermal motion by a specific proportion. Such substances are conductors. where there are two dimensions of rotation in space. As in many of the elements of division 4, the thermal motion, which requires two open dimensions because of the finite diameters of the moving electrons, is necessarily in time. In this case, zero temperature corresponds to zero motion in time. Here the resistance is initially extremely high, but decreases with an increase in temperature. Substances of this kind are known as insulators or dielectrics. And now I've read that over many times, and I just don't get it. But perhaps you do, and you can explain it to me. But I don't see. I'm not grasping the relationship between the thermal motion and the rotations in time and space, apparently. So anyway, keep moving on. Where there is only one dimension of spatial rotation, as in division 3, the elements of greatest electric displacement, those closest to the electropositive divisions, are able to follow the positive pattern and are conductors. The division 3 elements of lower electric displacement follow a modified time motion pattern, with resistance decreasing from a high but finite level at zero temperature. These substances of intermediate characteristics are semiconductors. For the present, we will be concerned primarily with the resistance of conductors, and will further limit the discussion to what may be called the regular pattern of conductor resistance. A limitation of this kind is necessary at the present stage of the investigation because the large amount of uncertainty in the experimental information on the resistivity of the various conducting materials makes the clarification of the resistance relations a slow and difficult process. The early stages of the development of the reciprocal system of theory, prior to the publication of the first edition of this work in 1959, which were very productive in the non-electrical areas, made relatively little progress in dealing with the electrical properties, largely because of conflicts between the theoretical deductions and some experimental results that have since been found to be incorrect. The increasing scope and accuracy of the experimental work in the intervening years has improved the situation very materially, but the basic problem still remains. And that's definitely, a sticking point in some of Larson's work is that, he has his two fundamental postulates, and then from his postulates, he derives a theoretical universe. And then in books like this, he compares his theoretical universe with the actual measured universe of the legacy scientists. Really, I can derive my theoretical universe strictly from theory, and it matches up with your measured empirical universe. However, if the empirical universe is presenting incorrect answers, then that leaves the reciprocal system a little bit, misled. And ultimately, Larson has to go with just, okay, well, this is what my theory says. And, ultimately, the theory overrides the observations. I guess. it's hard to say, because you don't want to be like in denial about things, but certainly there is a history of making erroneous observations as well. And in some cases, the observations are not erroneous, but they are just of limited accuracy. Okay. Ideally, it should be possible to deduce all of the pertinent information from theoretical premises alone within reference to experimental determinations. But as a practical matter, this is not feasible. A few steps can be and have been taken on a purely theoretical basis, particularly where the previous development of the theory has cast some important new light on the subject matter. But from the practical standpoint, an extensive and detailed investigation in any area is possible only if the theoretical study and the checking of the theoretical conclusions against experimental and observational data go hand in hand. It follows that where empirical data are lacking, progress is difficult, and where they are seriously wrong, it is essentially impossible. Okay, Larson just in a more articulate way said what I was trying to say there before. He can't really make a lot of headway when the empirical data that he's comparing his theoretical universe with is wrong, especially if he doesn't know that it's wrong. So, going on, unfortunately, resistance measurements are subject to many factors that introduce uncertainty into the results. The purity of the specimen is particularly critical because of the great difference between the resistivities of conductors and dielectrics. Even a very small amount of dielectrical impurity can alter the resistance substantially. Conventional theory has no explanation for the magnitude of this effect. If the electrons move through the interstices between the atoms, as this theory contends, a few additional obstacles in the path should not contribute significantly to the resistance. But as we saw in chapter 9, the current moves through all of the atoms of the conductor, including the impurity atoms, and it increases the heat content of each atom in proportion to its resistance. The extremely high dielectric resistance results in a large contribution by each impurity atom, and even a very small number of such atoms therefore has a significant effect. Semiconducting elements are less effective as impurities, but they may still have resistivities thousands of times as great as those of conductor metals. The resistance also varies under heat treatment, and careful annealing is required before reliable measurements can be made. The adequacy of this treatment in many, if not most, of the resistance determinations is questionable. For example, G.T. Meaden reports that the resistance of beryllium was lowered more than 50% by such treatment, and comments that much earlier work was clearly based on unannealed specimens. Other sources of uncertainty include changes in crystal structure or magnetic behavior that take place at different temperatures or pressures in different specimens or under different conditions, often with substantial hysteresis effects. Ultimately, of course, it will be desirable to bring all of these variables within the scope of the theoretical treatment. But for the present, our objective will have to be limited to deducing from the theory the nature and magnitude of the changes in resistance resulting from temperature and pressure variations in the absence of these complicating factors, and then to show that enough of the experimental results are in agreement with the theory to make it probable that the discrepancies where they occur are due to one or more of these factors that modify the normal values. Inasmuch as the electrical resistance is a product of the thermal motion, the energy of the electron motion is in equilibrium with the thermal energy. The resistance is therefore directly proportional to the effective thermal energy, that is, to the temperature. It follows that the increment of resistance per degree is a constant for each unmodified substance. A magnitude that is determined by the atomic characteristics. The curve representing the relation of the resistivity to the temperature in application to a single atom is thus linear. Like the curves representing the temperature variation of the properties that we examined in the earlier chapters, and for the same reasons, the initial level of the resistivity curve is negative. From this initial level to the melting point, the resistivity of an unmodified atom, one that has not undergone a structural rearrangement or other change that modifies the resistance relations, follows a single straight line rather than a curve composed of two or more segments of different shapes, as in the specific heat and thermal expansion curves. This limitation to a single line is characteristic of the electron relations and is due to the fact that the electron has only one rotational displacement unit and therefore cannot shift to a multi-unit type of motion in the manner of the complex atomic structures. A somewhat similar change in the resistivity curves does occur, however, if the factors that determine the resistance are modified by some rearrangement of the kind mentioned earlier. As P.W. Bridgman commented in discussing some of his results, after a change of this nature has taken place, we are really dealing with a different substance. The curve for the modified atom is also a straight line, but it is not collinear with the curve of the unmodified atom. At the point of transition to the new form, the resistivity of the individual atom abruptly changes to a different straight line relation. The resistivity of the aggregate follows a transition curve from one line to the other, as usual. At the lower end of the temperature range, the resistivity of the solid aggregate follows another transition curve of the same nature as those that we found in the curves representing the properties discussed earlier. The relation of the resistance to the temperature in this temperature range is currently regarded as exponential. But as we saw in other cases of the same kind, it is actually a probability curve that reflects the resistivity of the diminishing number of atoms that are still individually above the temperature at which the atomic resistivity reaches the zero level. The curve for the solid aggregate also diverges from the single atom curve at the upper end, due to the increasing proportion of liquid molecules in the solid aggregate. In this case, again, two values are required for a complete definition of the linear curve. Either the coordinates of 2 points on the curve, or the slope of the curve and the location of one fixed point. A fixed point that is available from the theoretical premises is the 0 point temperature, the point at which the curve for the individual atom reaches the zero resistance level. The theoretical factors that determine this temperature are the same as those applying to the specific heat and thermal expansion curves, except that since the resistivity is an interaction between the atom and the electron, it is effective only when the motions of both objects are directed outward. The theoretical 0-point temperature normally applicable to resistivity is therefore twice that applicable to the properties previously considered. Up to this point, the uncertainties in the experimental results have had no effect on the comparison of the theoretical conclusions with experience. It is conceded that the relation of resistivity to temperature is generally linear, with deviations from linearity in certain temperature ranges and under certain conditions. The only question at issue is whether these deviations are satisfactorily explained by the reciprocal system of theory. When this question is considered in isolation, without taking into account the status of that system as a general physical theory, the answer is a matter of judgment, not a factual matter that can be resolved by comparison with observation. But we have now arrived at a place where the theory identifies some specific numerical values. Here, agreement between theory and observation is a matter of objective fact, not one that calls for a judgment. But agreement within an acceptable margin can be expected only if 1, the experimental resistivities are reasonably accurate, 2, the 0-point temperatures applicable to specific heat, which are being used as a base, were correctly determined, and 3, the theoretical calculation and the resistivity measurement refer to the same structure. Table 24 applies equation 7.1 with a doubled numerical constant and the rotational factors from table 22 to a determination of the temperatures of the zero levels of the resistance curves of the elements included in the study, and compares the results with the corresponding points on the empirical curves. The amount of uncertainty in the resistivity measurement is reflected in the fact that for 11 of these 40 elements, there are 2 sets of experimental results that have been selected as the best values by different compilers. In 3 other cases, there are substantial differences in the experimental results at the higher temperatures, but the curves converge on the same value of the zero resistivity temperature. In a situation where uncertainties of this magnitude are prevalent, it can hardly be expected that there will be anywhere near a complete agreement between the theoretical and experimental values. Nevertheless, if we take the closer of the 2 best experimental results in the 11 two-value cases, the theoretical and experimental values agree within 4 degrees in 26 of the 40 elements, almost 2/3 of the total. The rare earth elements were not included in this study because the resistances of these elements, like so many of their other properties, follow a pattern differing in some respects from that of most other elements, including a transition to a new structural form at a relatively low temperature, accompanied by a major decrease in the slope of the resistivity curve. Because of this low temperature transition, it is difficult to locate the 0-point temperature from the empirical data, but in 9 of the 13 elements of this group, for which sufficient data are available to enable an approximate identification of this temperature, it appears to be between 10 and 20 degrees Kelvin. The theoretical range for these elements, as indicated by the factors listed in Table 22, is from 12 to 20 degrees Kelvin. Here again, then, the measured resistivities of 2/3 of the elements are at least approximately in agreement with the theoretical values. The existence of this amount of agreement, in spite of all of the influences tending to generate discrepancies, is about as good a confirmation of the validity of the theory as a general proposition as can be expected under the existing circumstances. Furthermore, it is not unlikely that there are alternate resistance patterns that result in explainable deviations from the calculated values, and some of the larger discrepancies may be thus accounted for when an investigation of broader scope is undertaken. Okay, now he goes into Table 24, which is temperatures of zero resistance. So I guess this is the temperature at which superconductivity ensues, or not exactly sure. But he's doing the same thing that he was doing in Chapter 7. This is a table from Chapter 7. And he shows the rotational factors of each atom, and then the calculated and observed temperatures of zero resistance. And as he said, looks like most of the values are quite close to where they are supposed to be, but there are quite a few exceptions, and some of them are kind of glaring. Here he predicts for indium that the temperature would be 48 degrees, and the actual result is 19 degrees. He's off by, again, not necessarily off, because it could be the empirical results that are off. So it's hard to say. But anyway, we will examine this table a little bit more in tomorrow's episode, and then we'll move on to the next part of this chapter. Again, if you are confused, you need to watch one of my first 474 videos on this subject to get yourself up to speed on the reciprocal system, because in future videos we're not going to be going over it. We're just going to be getting right into the content. Okay, thanks for tuning in, and have a great